There's some other stuff. So there's a story to this. So let's first look at the code. I have this is like a linked list thing. I didn't put any payload in, but you get the idea. And I have this code. I have this code that does some pointer manipulation on the list. So this is like a remove or something. I just wrote something. It doesn't make sense, but you get the idea. This is the code that's generated for this void foo. And you can see that there's two moves that read and dereference next. So I told you that the compiler does common sub-expression elimination. So why doesn't it do it here? And the problem is that this next that's written here, the pref could point to n, and then the next would change. So this is called aliasing. In C, usually if you have any kind of pointer stuff, then the compiler cannot know that this statement doesn't change this next. And there is, if it's function arguments, then there's some way to declare this in C99, but this is the one place where common sub-expression elimination actually makes sense to do manually. So in this case, if you know it's not changing and you use the same thing, then in this case would be one of the few examples where you could actually help the compiler. Yeah, but that doesn't help in struct definitions. The restrict is exactly what I meant for function arguments, but in this case, so that's why I chose this example. So this is called aliasing, and this is one of the reasons why Fortran is considered to be superior for mathematic code, because Fortran doesn't have pointers and no aliasing, so the compiler can just assume that there will be no aliasing. One of the other things that people are hoping the compiler is doing for them is removing dead code. And the compiler and linker actually have some, they make some attempt to remove dead code. For example, if there's unreachable code within a function, so for example, you have a switch statement and you check for one element twice, then the compiler detects this, will probably emit a warning and not generate code for the second one. Or if you have like a break in a function and then another statement below that, or a go to somewhere and then print whatever, then the compiler will know the print can never be hit and not generate code for it. So the compiler can do this within a function. And if it's a static function that's never referenced inside the same file, then the compiler can just remove it from the object file. But if you have a function that's not static in some object file and it's not used by someone else, but some other part of the object file is used by someone else, then the compiler has to leave it in. So you can either have the whole object file used or you can have not used, but you cannot use a part of it. And that's because the object files are more general than the C language needs. So you could have, for example, inline assembler that calculates some offset manually and then jumps somewhere and does reach the print or something. So there could be reasons like pointer arithmetic on function pointers, stuff like that. So the linker doesn't know that, you're not using that. And so if you write a library, you should put every function in its own object file, so this optimization can work in the linker. Note that function pointers do count as references, even if the pointer itself is never used. So the inline assembler is another thing that people tend to like to use. And what's saving us from this most of the time is that it's really hard to use the inline assembler in GCC. So if you looked at the manual, that's a pain in the ass, and most people never really get to it. So if you do something wrong, then the compiler will use your inline code, but will assume that the register you used was not touched, and then put some value in there. But only after you change something else in the code, and suddenly the result after the inline assembler statement is wrong. Or you can have stuff like the inline assembler statement is moved along because you forgot to declare that it modifies memory, and the compiler thinks, well, it doesn't do anything, so I can move it around. So most people cannot do inline assembly in GCC, and that's a good thing. So most of those who can do it don't actually improve performance with it. So the case in point in this instance is Matplay, which is an MP3 player, and this is the code that shipped with Matplay, and I think it still ships with it. So if you read for example, the AMD optimization manual, this is like an ancient instruction that was used to have 64-bit arithmetic and do a shift on it. And it still makes sense to use it if you don't have any temporary register. But if you do have a temporary register, this sequence is much faster. So what this does, actually it turns out that the guy used this statement not to make something faster, but because he didn't know how to do it in plain C. And there is a way to do it in plain C. So just this change from this statement to these three statements had a 30% performance impact on all computers I had access to. The guy wrote me that he has a Pentium 4, and on that architecture has the same speed. So apparently there's no fault for him on this point, but you should read all the manuals and try to make code run fast everywhere. So, oh, and this is what I mean when I say it's hard to do inline assembly right. This is still could be considered wrong because there's no volatile here. So the compiler could still try to move the statement around and break something with it. But I'm just mentioning this so you can see this actually, everything of these is actually needed here. So, and this is how you would do it in C. I used the same identifiers, that's why the underscores are here. I'll show you again this one. So you have low, high, and result. So this is how you would do it in C, and this is the code that the Intel compiler generates. And if you look closely, you can see it's the same code that my improved version of the inline assembler statement would have used. Unfortunately, GCC sucks with 64-bit arithmetic on 32-bit platforms. So with GCC, you didn't get this good code. You actually get the SHRD using code. But that's what I'm saying. You should always look at what your compiler does. But you could have done the same thing without inline assembler and it would still have worked just as fast as the current shipping version of Matplay. Another thing, this is the first time I actually understood that inline assembler is not necessary. So the Intel and most other architectures have instructions to rotate the bits inside the word. So for example, if you shift something, you will fill the new bits that are, if you shift left, then by 4 bytes, then you have 4 bits, then you have 4 new bits on the left, and they will be 0 filled. And rotating just means that the bits that fall off the right side get put in on the left side. So that's something you rarely use, but sometimes people need this, and there is no way to express this in C in a good way. So what you have to do if you use C is you have to do the shifting and ORing yourself. And it turns out if you do that, the compiler detects it and generates the OR for you. So there's, again, no reason to use inline assembly here. And this looks pretty hairy, but as you can see, the compiler is usually smarter than people give it credit. So this is more of a C++ thing, but it also makes sense in C with older compilers. If you do an A++, what the hell? Shut up. So if you do A++, the compiler usually has to create a temp copy of A, which it usually doesn't in C because it's built-in types like int or pointers, and then the compiler can do it usually without creating a temp copy. But in C++, this actually makes sense to use ++A instead of A++. This advice was also good for C in the 90s, but today, even in C++, it doesn't matter. So let's come to the optimizations that do matter. And one of the optimizations that actually do matter has to do with cache lines. So in the CPU, there are several levels of cache, and they usually have cache lines and associative caches. You can read up on this in CPU architecture books. So the point to understand about this is that several pieces of memory map to the same cache line in the cache. So if you have a data structure that has the same size as the cache line, and you walk through the cache, your array, then it might be that every element of the array actually hits the same position in the cache line, and you lose all the cache efficiency. And this is known to happen in big matrix multiplication code that they use to benchmark supercomputers. So this is why this is well known. And the thing you have to do if that happens is to add dummy byte to each element in the array, and then it won't align anymore and it will be faster. So this kind of thing is something the compiler could be expected to do, but doesn't right now. Fortran compilers on supercomputers are known to do this, but I know no C compiler that does it, in particular not GCC. So there's some optimizations I'm saying that actually do make sense, but most of them don't. So my personal pet peeve is people who just coming from university know every fancy algorithm there is, and they have this, you give them the task to sort 100 file names in LS, and they use like a self-balancing whatever tree with like, I don't know, and usually this is like several screen pages of code that you just would have to read, and it not only doesn't it make it faster, it also has more overhead because trees have next pointers and left pointers and child pointers, and all of this stuff pollutes the cache, and in reality it's usually fastest to do it the simple way. So if you see someone use Fibonacci heaps, just shoot them, okay? If you do manage 1 million elements, then you should use a proper data structure. But that's so rare that, in most cases, don't. So my rule of thumb is if the data structure can't be explained on a beer coaster, then it's too complex. The only actually really important optimization goal these days is memory latency. And I have these values for you. If you use multiply instead of shifting, which I showed you the compiler already does for you, fixes for you. But if the compiler wouldn't do this, that would be a 5-cycle penalty. I showed you the call penalty is 4 or 3 cycles, depending on the CPU. So 5 cycles if you use mul instead of shift. If you mispredict a conditional branch, it's 10 cycles. But if you access main memory and that's not in the cache, that's 250 cycles. So you can see all the stuff you do with, oh, let's make a shift out of this mul, that's really the utter wrong place to optimize. In most cases, you should try to make your code and data structures as small as possible so it fits in the cache. And if you have done this, then you can look at the rest. So keep this in mind when you do optimizations. There is some commercial profiling tools that try to tell you on which parts of your code have many cache misses, but AMD actually has one that's supposedly free and downloadable, but I didn't get it to work. It's maybe the Windows version works, but I don't develop on Windows, so I don't know. Intel has one that costs money. It might be maybe they give it away now too. They give away the compiler after all. I don't know. But this is really the only really important thing to optimize for. All the rest that people spend weeks and weeks of their life doing with inlining functions here and trying to restructure code there. Usually the only thing that actually matters is the main memory misses and cache misses. So that's basically all I have to say. If you do an optimization, test it on real-world data, and if it doesn't work, undo it. So if it's not drastically faster, but just a little bit faster, but made the code unreadable, undo it too. Because usually, the people won't even notice the difference in speed, but they will notice if the code is unreadable, because then security problems will not be found and will hit you later when you can less afford them. Any questions? Okay, so one?
Actually, not a question, but a comment about cache misses. Valgrind should have a tool for it, CacheGrind.
Oh yeah, you're right. Valgrind has one. That's right. Is it any good? I've never used it. I just know it exists.
Didn't try it either.
Yeah, I don't know. So that's right. Valgrind actually has one, has a tool for that. And everyone should be using Valgrind anyway. Plug. So use CacheGrind too.
Any more questions? Ah, there.
I put the slides on the webpage and upload it to the Congress web pages too, so don't worry. If you missed anything, you can still email me. And a full house.
There's a GGC extension, as far as I know, called likely or unlikely, which you could use in conditional statements. Did you make any research on that, or can you give recommendations?
I've never used it, so it might be interesting. Can you email me a link or something? I'll check it out and put it on the webpage too.
Okay, I will do. Thanks.
Okay, thank you.